All right, the audio should be working this time, and we'll be redoing exam 2. For the problem, we're just going to go over it again, and we're going to have a network of pipes. It's going to calculate the water flows through each pipe segment, and then we're going to end up calculating the net flow in and out of the node sources, which is node 0, and the sink node, which is the exit node, node 4. And we're going to assume all elevations are at 0, except for node 0, which will be at 30, and node 4 will be fixed at 0 pascals, while node 0 will be set to 200 pascals. And then we'll have all the diameters, we're going to say, are 0.1 meters, and we're going to have a relative roughness of those pipes of 0.001. And we'll also have this pipe array outlined here. So I'm just going to go to the problem in my OneNote. So we're going to have, we can see that right here, pipe 0 will be at 30 meters, and we'll have the pressure at 200,000 pascals. All the elevations will be 0 except for node 0, which will be 30 meters, which I outlined right here. And then we will also have all pipe diameters 0.1 underlined here, and then we also have our array of our pipe flow, which is this is what it's going to look like when we actually hard code it out. And it will be, so you can see the first value 0 will be our which node it's coming from. The second value 1 will be which node it's coming to. Third value will be our length of the pipe, and then the fourth value will be our K value, which is the fittings of the pipe. So that's just outlining our problem. This will be our array. This is what our system of pipes looks like in this picture I've drawn here. And so we're going to go ahead and just head over to Colaboratory, and we're going to first just set our imports. So we're going to go import numpy as np, and we'll just shift into that. And then we want to set our variables, which will have g. We can say this is equal to 9.81. We'll have the density of water. We'll have the density of water, which will be rho. We're going to say that this is 1,000. And then our viscosity, mu, that will be 0.001. And then our diameters, we said that they're going to be all 0.1, so 0.01. And then our relative roughness, ED, in this case, we'll make 0.001. So that's our initial imports. And then now what we're going to do next is we're going to need to look at the Bernoulli's equation in order to calculate what we want to do. And so now looking at Bernoulli's equation, we're going to go back to our notes here. We can see we have P2 minus P1 over rho g plus Z2 minus Z1, the change in height, plus K plus 4 times F, which is the friction factor, times the length over the diameter, times velocity squared over 2g, acceleration due to gravity, and that will be equal to 0. So that is coming from our Bernoulli's equation. And we're going to say this expression right here, this is going to be our delta head. We'll just actually write it. We'll just say this is going to be what we're going to call our delta head when we get there. And we know that we have our K values, fittings values. We have our length times our diameter. We have our velocity. If velocity is known from over here, we also can calculate our flow rate using this expression over here. But what we don't have is we don't have this F, this fanning friction factor, in which we're interested in. So what we need to do is we need to use this Churchill correlation right here, and this will help us calculate F, taking in our relative roughness and our Reynolds number. And right here we also have our Reynolds number, which is equal to rho VD over mu, which is the mu being the viscosity. So we're going to go back to Colab, and we're going to need to calculate a function that's going to end up calculating our fanning friction factor F. In order to do that, so we can start a function. We'll just call this F. So it's going to take in arguments Reynolds number and relative roughness, which is ED. And then enter. And from our equation, in the Churchill's equation, we can say that this is what A is equal to, and then B is equal to this. So we're going to go ahead and code those in. So we have A equals 2.547, I believe. Yes, 2.547 times log, which is we're going to use np.log to do that. And then we have, let's go back and check again, 1 over, and then we have what, 7 over Reynolds number times 0.9. So we have 1 over 7 over the Reynolds number. And that will be to the 0.9. So exclamation or exponent 0.9. And then what's next? We have plus 0.27. And then we have times our relative roughness ED. And then that will all be raised to 16. So we can go ahead and do that next. So raise all that to 16. Shift enter that. Should be good, okay. And then our B is a lot simpler, which we said was 3, 7, 530 divided by our Reynolds number. And we'll go ahead and put parentheses around this as well. So that will be our B from using the Churchill's equation, or Churchill correlation, I guess. Churchill's equation, same thing. And then we want to, what we want to return, in this case, is our fainting friction factor. So in that case, we can return this right here, this F, which took in the arguments of A and B and put them through. So we'll have F equals 2 times 8 over the Reynolds number. And then we have, that will be raised to the 12th. And then we'll have that added to 1 over A plus B to 3/2. So that's added to 1 over A plus B. And then that will be raised to the 3/2, which is 1.5. And then this will all be raised. This entire expression, besides the 2, will be raised to the 1/12. And that should calculate B. So if we want to see, we can see what F might be. Give a Reynolds number, we'll just give it a high number. And then a relative roughness, we'll just say this is ED, shift enter. Do we shift enter that? Do not think we did. Okay, let's try again. Okay, so there's an example of what a fainting friction factor might be if we give our Reynolds number as 3,456, just making sure the function works. All right, so now what we need to do is we're going to write another function, and basically if we go back to our notes here, we need to write a function that is going to calculate our delta head, which is this left-hand side of our equation right here. And it's going to take in our flow of our flow. It's going to take in length, which we know, diameter, and our fittings value, as well as our relative roughness. And then we will put in our equation for velocity given flow, which is this Q over pi d squared over 4. And then we also put in our Reynolds number equation, which is our rho Vd over mu. So we need to go back to Colaboratory, and we can create a function for this delta head. So we'll call this, we'll just call this d head, and it's going to take in our flow. It's going to take in our length of our pipes. It's going to take in our fittings value. Okay, and then it's going to take in our diameter, and it's going to take in our relative roughness. And then we will put in our equation for velocity, and in this case we said that this was, go back to our notes, Q over pi d squared over 4. So we have Q over, and then we have pi, so mp dot pi times our diameter squared, and then this will be over 4, and that should be good for that. And then we also put in our Reynolds number, so this will be our rho. This will be times our velocity, and then times our diameter, and then divided by our viscosity mu, and then enter. And then we want to return our delta head. So this will be the negative of the equation. So we'll put this onto the other side of 0. So it will be minus our k plus 4 times f, fittings value, which we just made the function for with the Churchill, and over length times diameter times length over diameter times our velocity squared over 2g. So what we're going to do next is we'll go negative, put that in, so we move to the other side of the equation. So we'll have negative k plus negative k plus 4 times f, and our f is going to take in our, remember our f is going to take in our Reynolds number and our relative roughness to calculate it using the Churchill's equation, and then times our length over our diameter, and then this will be multiplied by our velocity, which is our v squared over 2 times g over 2 over g. And this should be good, I think. Let's go ahead and test it so we can see our what our delta head will be. So we have our d head, and if we put in a value of flow, we can just call our flow 2, length say 1, k, you can say like 1.5, and then we have our diameter, which is 0.1, and then a relative roughness 0.001. Shift enter. Okay, so that will be our delta head given these values. But we want, and this will be the delta head from the from node to the to node. So where the flow is coming from to where the flow is going. And so if our delta head's negative, we want our flow to be negative, and then vice versa. So we can make our flow negative, and we want to make our delta, so this will check to make sure our delta head's negative, or our delta head's positive, which it looks like it is not. Not sure why we're getting that value, but you can see, so we flow, length, k value, d. Don't know if we need to make, do we need this, can we say this is ed? Okay, so if we have our negative flow, and it is not changing, but to fix this, you can see that if we have a negative flow, it's going to end up giving us a negative velocity, which will then give us a negative Reynolds number, and we do not want a negative Reynolds number because it's not possible. So basically, to account for this, we need to just basically change the sign in our equation. So we're gonna, to do that, first we need to make sure this is set into absolute value. So we're gonna do a numpy import an absolute value, and that should make it so our velocity should be always positive. But if we want a negative velocity, this isn't going to work. So you can see that we're not getting that weird number, but this sign isn't changing because our velocity is always positive. So we need to recorrect this sign down here when we actually return our delta head value from the other side of the equation. So we're going to do the np.sign. So this will readjust our sign, and this will readjust our sign for flow. So we'll make it the opposite of what it was, what it got adjusted to, and then we'll just multiply this by that. And that should be able to give us opposite delta head with opposite flow. So let's go ahead and try this. So we have, okay, so that's the same number, and now we make our flow negative. And yep, so now that our flow is negative, our delta head is positive, and which that's what we want. So this changing these signs allowed us to readjust in order for us to get a non-negative Reynolds number, because when we get a negative flow, we get negative velocity, which then makes us get negative Reynolds number, and we don't want that. Okay, so now we have this function for delta head that calculates our delta head in our Bernoulli's equation, which was that left side, which the pressure drop was the elevation change. But now what we want is a function that we can use to calculate our flow. So instead of just having a function that calculates our delta head from given flow and given velocity, our velocity equation and stuff, we even want to make another function that can calculate our flow. And basically what we want to do is we need a function that will calculate our flow, and then this function will end up taking in our delta head in order to calculate our flow. So we'll just call this function flow because it's going to be calculating flow, and we know it's going to be taking in our delta head. But in this case, since this function is already called dHead, we need to call our delta head something else. So we're just going to call it delta head. I always do that with the second capitalization. And then we also know that this will take in our length, and it'll take in our value of fittings, so pipes, take in our diameter, and it's also going to take in our relative roughness, ED. Put a colon there, and then it also is going to calculate our velocity and Reynolds number given these arguments right here. So we can just take these equations from up here, and we can go ahead and copy them down into this space, and I think that should be good. They should be indented in the function. Okay, and it's going to return basically our Bernoulli's equation, return our flow. So we can go return, and we're going to, if we go back to our notes here, so we're just going to be returning our Bernoulli's equation in terms of flow. So we'll have our delta head. This will be our delta head, and then we'll add that to our at the second side of the equation, and which is right here. So I believe we can just go ahead and copy and paste that over, and boom. And so it should be returning our delta head in terms of flow, and we make sure these parentheses are lined up correctly. Okay, yep, so we'll return our delta head in terms of flow, or not, sorry, we'll return our flow in terms of delta head and our given these arguments up here, as well as our velocity and Reynolds number. And basically what we want to do is we're going to eventually need an initial guess for Q in order to do this. But basically what we want to do is, we can go ahead and shift enter this, but we need to drive this equation, our Bernoulli's equation, to 0, because you can see in here that it is equal to 0 from our notes right here. But basically what we are going to want to do is we want to drive this equation to 0. So to do that, we're going to need to make a new function that will drive it to 0. And then to do that, we're going to use something called the Newton's method, which will basically take an initial guess of our flow, or yeah, it will basically take an initial guess of our flow, and we're going to end up driving this function to 0 in order to get it lined in with our equation. So we're just call this function f to 0, and then this will take in our flow. So because that will be our initial guess that we're going to supply, and then we can go ahead and copy and paste these once more again. Oh, go ahead and copy and paste these again. So we'll put these in order to drive our flow to 0, or our Bernoulli's equation to 0 given flow. We're going to need to recalculate our V and as well as our Reynolds number. And yes, we have our absolute value there as well, just making sure. And then we can now return our delta head. So we're going to want to return our delta head plus our k plus 4, since this will be calculating through our flow. So we can return that, and we can get rid of this. And once we have our flow defined up here, this is going to end up returning our resulting flow rate. So we can just go ahead and call this resulting flow underscore rate. So that's what that's going to return once we have a good initial guess for our flow rate. But to do the initial guess, like I said before, we're going to need to make a new import up here. And that is going to be using the Newton's method in order to make drive our Bernoulli's equation to 0. So to import the Newton's method, we just do from scipy dot optimize, I believe it is. Yes, and then we import our Newton's method. So we import Newton. And that will allow us to, once that's imported, that's going to allow us to, given a good initial guess for our flow, which is Q, that is going to allow us to drive our Bernoulli's equation to 0 in order for us to get the values that we want. All right, so we're gonna just go ahead and test this function to make sure it works. So I'm gonna just we'll just go ahead and define a delta head value, and we'll just call this like 40 or something. We'll say RL is equal to 10 or something. K, we can just say like 1.5 again, and then we have our diameter and relative roughness as well, but we can just say F20. And then if we take in a flow, we can just say if the flow is 2, delta head. Let me go ahead and run all real quick. I think this should just be D head. Okay, actually we need to have, no, what we need to do is delta head was set equal to 40. That's what we need to do. Okay, so that will basically go say resulting flow for our function that's going to calculate, just to make sure that works. But what we need to do to basically drive this equation to 0 is what we need to do is we actually need to make an initial guess for our Q. In order to do that though, what we're going to need to do is we can go back to our equation. Is it's kind of hard to make an initial guess for just Q, but we can use Newton's method to make an initial guess for something else. So basically what we're going to want to do is, since it's kind of hard to make an initial guess, like a good initial guess for Q, that's going to drive our Bernoulli equation to 0. We can basically, what we're going to do is we're going to put Q in terms of V right here, in which we got from our Bernoulli equation. So we just said that V, this was equal to V right here. So we isolated for V, and then if we multiply by our pi d squared over 4, that will be equal to our flow Q. But basically, what I was saying was it's kind of hard to get an initial guess for Q alone. So what we can do is get an initial guess for our Fein friction factor, because basically we can go back over here. Basically, from the diagram, if we look up this Moody diagram, you can see kind of, we'll just go to an image. You can see on this Moody diagram right here that, I'm going to wait for it to load. Okay, so basically you can see over here our relative, our friction factor over here is only in a small range of values. So if we kind of pick a value close to in the center, in this case we can kind of just pick this 0.01. This will allow us to basically have a good initial guess for Q if we put all of these numbers in terms of our flow. So that's why we can actually make an initial guess for Fein friction factor in order to drive our Bernoulli equation to 0. So now what we're going to want to do is we go back over to our network flow, and we can just say that our initial guess for Q can just be we can call it Q guess, and we know that our Q guess will be equal to this equation right here. This will be our initial guess for Q, so we can just go ahead and put that in there. So we have our Q guess, that will be the np.pi, so we can actually go back in here and just copy and paste that so we don't make any silly errors. So np.pi times diameter squared over 4, and then we can multiply that by the square root of this equation right here, our negative delta head over k plus 4, and then put our Fein friction factor in there. So we can go ahead and go np square root, and then we have our negative delta head, delta head, did it again, and then divided by, and we'll have our k plus 4 times the fanning friction factor, which we can put in directly, which our initial guess is going to be 0.01, and then times our L divided by our diameter. And then this will be multiplied by 2, let's go back, yes, multiplied by 2 times G. And this will give us a good initial guess for our flow. So basically what we want to do now is we can go ahead and test this. And we can just say, test this with the Newton's method. So we'll say Newton, and then we have our function that we're driving to 0, so f to 0. And then that's going to take in our initial guess, x is 0, which you can see right here, which will be our Q guess. But when we give an initial value of 0.01 to fanning friction factor, this will allow us to calculate. So we'll go ahead and have that. It seems that we're getting an error right here. Let's see, failed to converge after 50 iterations. Not sure what I'm doing wrong here. Is that because that's negative? Okay, I think that is because that is negative. So we'll need to change that, but we can check our Q guess. And we can see that it's pretty close. So this actually is calculating pretty close in value to what we need. Okay, so now to make this these functions run a little bit smoother, we can go ahead and put our basically to make these run a little bit smoother and finish our flow function. Since we just have this right now, it doesn't really calculate anything. We can put our function that drives the Bernoulli's equation to 0 inside of our flow function. So we're going to go ahead and do that, and Control V that. Just make sure these are in there. And then we can also put in our initial guess for Q inside of our flow function in order to drive it to 0 using the Newton's method. And we'll put that above here. So we'll put that in there. And it'll give itself a little bit more space to see that. Shift enter that. Unexpected indent. Okay. That should be good right there. And then we also need to put in what this resulting flow rate is going to calculate. So we know that this flow function is going to calculate a resulting flow rate using the Newton's method. So we'll have our resulting flow rate. We'll have our resulting flow rate, and that's going to equal our flow calculated using the Newton's method. So we have our Newton, and then our imports will be our f to 0, which is going to drive it to 0. F to drive our function to 0, and then we'll have our initial guess, which is our flow. So, and then we have Q guess. Shift enter that. And if we want to go off and test this, Q guess is not needed down here anymore. We can go off and now test this. So we'll just shift enter this, shift enter, X this out, X that out, X this out. Okay, so now if we want to just test this, we can go ahead and just test our flow function. So we have flow, and this is going to take in arguments of our delta head. So we have our delta head, we have our L, our fittings value, our diameter, as well as our relative roughness. So we're going to go ahead and see that this calculates. Resulting flow rate is not defined. Do we run that? Do we calculate it? Resulting flow rate equals Newton. Yes, okay. it should be defined. Okay, so it seems to be working now. I'm not sure. Okay, resulting flow rate is not defined. Okay, this needs to be indented. Now I believe it should work. Okay, yes. So now we can see if we have a negative delta head, flow should be negative, flow should be positive. Since our delta head is we define right here is 40. If we have a negative delta head, flow should be positive, positive delta head, negative. Okay, so now it's failing to converge. Okay, so this is what I was talking about a little bit earlier. So now we basically need to adjust for the directionality of our delta head, and this will make it so we don't get another negative Reynolds number. So what we need to do is we need to alter the sign of delta head. So how we're going to do that is in our flow function, we basically need to do another one of those absolute values. So we can say we can just call this our delta head for absolute value. So DH underscore absolute value. We'll just say it's equal to the absolute value of our delta head, so we don't get a negative Reynolds number once again. So we have absolute value delta head, and that should fix our issue. Boom, 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 and boom, boom, boom. Okay, so it seems that it's not fixing our issue yet. Okay, yes, so since it's always going to make a positive delta head up here, we also need to do what we did up here in our d head function, and we need to multiply our resulting flow rate back by the sign of our delta head to readjust for the directionality. So what we're gonna do is we'll do np.sign of our delta head, and then we'll multiply that by our resulting flow rate, and that should fix this issue of still failing to converge. Do we need a negative there? Okay, it seems to still be failing to converge. Let's see. Don't think we need a negative there. Should fix our issue though. Do we need a negative here? Okay. Do not think we need a negative there. Absolute value for delta head. Turn delta head, the resulting flow rate is equal to Newton. Then we readjust for the sign. So our sign of our delta head times resulting flow rate should make our flow. Okay, well if this is a negative delta head, it seems to work. But that does not seem, that makes it so our delta head is the same sign all the time. So I'm gonna do a quick cut. Okay, so we're still failing to converge. Value is 0.12. Okay, so that's the right value. Okay, so we can go ahead and replace these delta heads by what we just did, our DH underscore absolute value. And we have another one right here, DH underscore absolute value. Okay, so that replace our delta heads. Does that fix it? Because I think there's a negative in the square root there. Does this fix it? Let's check now. Okay, so it looks like it's still failing to converge. Okay, are we missing a negative? I feel like we're missing a negative then. Does there need to be a negative here? Okay, boom. Awesome. Okay, so now that we have since our delta head's negative 40 here, we'll just make it 40 so there's not confusion. So if our delta head's 40, our flow will be negative 0.12. If our delta head is negative, flow is 0.12. So we have opposite signs in flow and delta head, which we need. So that fixes that issue. So our flow function now works. It calculates that given a initial value for Fanning friction factor, uses the Newton's method to give a new initial value for our Q guess. It works to incorporate the directionality for our delta head, so we don't get a negative Reynolds number. And so now we have our delta head as well as our flow are now opposite signs in which we were needed. Okay, so now that we have our flow function, we can clean this code up a little bit. You can notice that in our d head function up here, we already have the v as well as the Reynolds number, or velocity and Reynolds number calculated. And we also have this expression in right here. And we also have it down here. So instead of returning that whole expression again, we can just go ahead and instead of returning our Reynolds number and velocity again, we're just going to go ahead and clean this up a little bit, and we can just go ahead and put our d head, not our delta head, our d head function in here. So we're just going to go ahead and, which is also our delta head, but it's called d head. And then so we can just go ahead and add this to our flow function. And so we have our flow, our length, pipes, fittings value of pipes, and our diameter of pipes, and our relative roughness of the pipes. So we can just go ahead and put that in there. I'm going to make sure that it works so it doesn't change any of our numbers up. And our flow, flow should still be negative 0.12 with a positive 40 delta head. And if we go ahead and just make sure the signage is right, so positive flow, negative delta head, negative flow, positive delta head. So now what we're headed next is we're going to actually put in our array of pipe system, and then we're going to be able to calculate our flows through each node and get the values that we need. Okay, to save time, I basically just typed this in while the video is paused. But basically we already had it written out anyways from the exam 2 prompt. You can see it was already written out right here. And we also wrote it out in our notes over here just to refresh our memory. So we have this array, which includes the from nodes, to nodes, so length, and the fittings of the pipe. So this is the array of the pipe flow that we went through, and this is the little picture right here that I've drawn. So we know we have this certain pipe system. But this is what the array will look like, and which we just hard-coded out. And I'll go ahead and actually, just so we can see it, and we can tell which index the array is for each index. So we have the first index, which is 0 in Python. We know that's our from node. So this is just rewriting from our notes. So we have our from node is the first one, and then our 0th one technically. To node is the second one, and then our length is the third one, and then our fittings value k will be the fourth one. So that's just outlining what is basically those numbers mean in our array. Okay, well, so now where we're headed is, well, basically if we think about it, what we want is we're going to want to be able to extract these numbers in a singular array one by one instead of just from this huge pipe array of data that we have here. So the values that we need are, we can first say, what do we need? We need our height, in which this case we said z's. If we go back to our notes, in this case we said all of our z's were 0. We need our external pressure, which will be this 200,000 pascals right here, and then at 4 we know that's 0 pascals, but we know that it's 200,000 pascals. And I'll go ahead and code this out as I'm saying it. It's just so we don't just have a moment of, like, a few minutes of silence while I'm coding these arrays out. But we said that we needed our height z, and in this case we can put this into its own array, NP array, and we said that in this case our heights for our first node, so it's node 0, it was 30, and then for the rest of them we said it was 0. So 1, that's 0, that's 0, that's 0, and that's 0. So our node 0, our node was 30, and then our node 1 was 0, node 2 was 0, node 3 was 0, and node 4 was 0. And we also need our external pressure, so that's at node 0. So we'll call that external P, and this will be in its array, and we'll specify that as the np.array, and then that will be, I shouldn't put a space there, that will be, I'm so bad at typing, that will be 200,000 pascals, so 2e to the 5th, and we said that the rest of, so the external nodes, and the pressure at the 4th external node, which is the other external node, which we just said was 0, so we're just going to write 0 there, because we only want the pressures for the external, and we'll get the internals later. Now what are our external nodes? So our external nodes, we said were 0 and 4, so we can put those into their array. So external nodes equal, and we said those were 0 and 4. And what else do we need? We need our from nodes, our to nodes, our length, as well as our fittings. So our from nodes in this certain array, we can say our from nodes, those will be in our pipe array, so pipes. And we know that this will be in the first column, but Python indexing starts from 0, so we just need to grab it from the technically 0 column. So we'll just do the colon and 0, and that will grab our from nodes from that column. And we need to make sure these are integers, so we need to make sure we put in this numpy function with as type, just converting them integer 32s, just to convert them to integers, so we don't make it decimals. And then we have our to nodes. We know that's our second column, which is in Python indexing, so our first index technically, not 0. So we know that's in our pipe array as well, and we can say that that is the colon and comma 1, and then that we also need to make sure is a integer, so we'll do this as type dot np32 as well. Once again, np.integer dot int32. Okay, so we will make sure that we have that there as well. Okay, enter. And what else do we need? Our lengths. We need our lengths. So that will be in our pipe array. Pipes, that will be the third column. So we have colon and 2. And then our fittings values, which will be our last one. And we'll have k is equal to pipes. And that will be in our 4th column. So technically, it'll be 3rd, because Python indexing, once again, starts from 0. And what else do we need? Our number of pipes we're going to need. So our number of pipes that we have, remember, it'll be different from the number of nodes, because there'll be 2 pipes connecting. So from 0, I'll just show the picture. So the number of pipes we're going to have is, look, 1, 2, 3, 4, 5, 6. So those are the number of pipes we're going to have, although we only have 4 nodes, so don't get those confused. So the number of pipes we're going to have will be pipes, and this will be basically this will be equal to the shape of our array. So we can just say shape of the first column, the from node, because each node it comes from, that will equate to one of the pipes. And then we need our pipe diameter, so pipe D, and this will be, we're going to use np.full to get the shape of the system we're talking about, the shape of the array we're talking about, and this will be the number of pipes. Before I actually do this though, let's make sure our number of pipes is at 6. Okay, let me delete that first. Let me make sure our number of pipes is at 6. Okay, yeah, so our number of pipes is at 6, so we're good. As well, I just wanted to make sure that was set before we moved on. So we have our end pipes, a number of pipes. Sorry, I did not, we already had number of pipes. Pipe diameter. So pipe diameter, that is going to be the np.full, in which we will now return a new array. Return a new array of given shape and type filled with a fill value. That's why it's the np.full. So basically our shape is going to be the end pipes. And then our fill value, which we were interested in, will be our diameter. and we'll do the same thing for the relative roughness. So we'll have pipe relative roughness, ED, and we'll do the np.full again. So np.full, and what is our shape? Our shape of the number of pipes we have, 6, and which value we're going to fill it with, and that will be our relative roughness. Okay, so this kind of we'll start to set up our arrays that we need in order for us to grab the values that we're interested in. And I'm just going to make sure that these work real quick. So we have our pipe diameter. Okay, so yeah, we can see that this put the diameters, in which we said they're all 0.1, into the array, or into our pipe array. So if we do the same thing for our pipe relative roughness, we'll just make sure that it works. Yep, okay, so this also put in the relative roughnesses in which we're interested in for each through each pipe, in which we said that all the relative roughnesses were 0.001, just like all the diameters were 0.1. So that looks good. And there's one other thing that we need. We need to specify the number of nodes we have. So we know that we have nodes 0 through 4, which make 5 nodes. But to do this, instead of writing just 5, because if we have larger pipe systems, we're going to want to be able to change this up without having to recode the entire thing. But basically what we can do is so we have our n nodes. We can say that if you look at this array right here, you can see that the maximum number of nodes will be the maximum in this second column were 2 nodes, since we're going from a lower node to a higher node. So the maximum number of nodes will always be in the 2 node column. So to basically implement that, we're going to use something in NumPy called npmax. Yeah, npmax. And this will basically return the max value in that 2 node column. Because if you have like a pipe system with like 100 to 1,000 different pipes, it's a lot easier to do it this way than typing just hard coding in some sort of number. So we have a npmax, and in our pipe array we'll have pipes, and since it's the second column, since Python indexing starts from 0, we have colon, comma 1. And then we want to also make sure that this stays as a integer. So we need to do the as type once again. So the as type np.integer 32 and shift enter. NumPy float object 64. It seems I have messed up somewhere. NumPy float as type. Oh, that is my error. I had 2 E's. As type. Okay. So let's just check this to make sure. Number of nodes. Okay. Right now it says 4. But we have to remember Python indexing is weird. It starts from 0. So we need to make sure we add this plus 1. And we add that 1 in order to get the correct number of nodes, which should be 5. Yep. Okay. So now we have 5. And we just needed to add that 1 because Python indexing starts from 0. And what we're going to end up doing next is, now that we have these arrays specified, so we can grab values out of our pipe array, out of our pipes, or just like our system, easily. Now that we have them in their own individual arrays, we can now make it a function to calculate net flows through each pipe. So that's what we're going to be doing next. Okay, so now we're going to calculate the flows through each individual pipe, and to do that, we're just need to create a new function, and this function is going to iterate through our different values of delta heads through each pipe. And from those iterated values, we're going to then iterate through our flow function, and then it will spit out our values of the flows at each pipe. So to do that, we're going to first start the new function, and we'll call this function calc_flows, since it's going to be calculating our flows. Make sure that it says calc, not clack. So calc flows, and since it'll be iterating through our heads, we're going to want it to take in the value of our heads, and we need to call this heads because we already have delta head, blah blah. We already have we needed a different variable name. So then we have flows, and this will so actually, since we need to iterate through the value of our heads, we need to first specify our head values, and then we'll put our flow function in. So since it's going to be iterating through the head values, we need to do for I in range of our pipe system, so n pipes. So for I in range of our pipe system, how many pipes we have, we want to do iterate through our head values. So iterate through our delta head. So we have our delta head, and that will be equal to and our head that'll be equal to our heads. And since it's going to be going from a node to a node, we're going to do the from nodes. We're going to iterate through from nodes minus the two nodes. So we're going to do heads, and then we're going to do the wrong thing. Should have braces. Heads, and then we have two nodes, and then we're going to iterate through those. So we need our I, and then we have the minus. Since it's the delta head, we need to do this the change in heads. So we have the heads from the from node, or the heads from the two nodes minus the heads of the from nodes. And we're also iterating through these from node values. And now I think we can put our flow. Now we put our flows in. So now we can put our flow insert our flow function. And since it's going to be iterating through our delta heads in our flow function, we also need to iterate through our flow function. So we need to include an I there. And this will be equal to, our flows will be equal to, so we have our flow function, and this is flow, not flows. And these will take in the arguments of, again, our delta head. We'll have our delta head, and since which we just calculated up here, iterating through the two nodes minus the from nodes, and then we'll need to iterate through our lengths. So we need our I there. And then we need to iterate through our fittings of the pipes values, our K. And then we need to iterate through our pipe diameter. And then last but not least, we need to iterate through our relative roughnesses of each pipe. That would be pipe underscore ED. And this should give us our flows through each pipe. So we need to make sure we indent there, and we have return, and then we can return flows. So we're going to go ahead and shift enter. To test this, we can go ahead and give us some arbitrary head values. So we can say heads equal to np.array, and then we can just say these heads are, I don't know, 50 first head, 40 the second head, 30 the third head, I don't know, 35 the fourth head, and then 10 or something. Shift enter those, and then now we can test. So we have calc underscore flows, and iterated through each of our heads that we just specified. This should give us an array of our flow values. Length is not defined. Length is not defined. Lengths is not defined. So we need to make sure that is spelled right. Shift enter, shift enter. Flows is not defined. Oh, right. So we need to specify an initial value for our flows. So to do that, we're going to just say, make sure our flows start from 0. So we'll have the np.zeros, and we'll make sure that in our pipe system that for number of pipes, the flows will start at 0. So that should iterate through, and boom. So those are our flow values that we will be getting through each pipe. And remember, this is through each pipe that we have. So from 0 to 1, 1 to 2, 0 to 3, and so forth. And what we're going to want to do now is we want to make another function that will iterate through and calculate the net flows at each node, nodes 0 through 4, and this will help us get to our answer. Okay, so now we can create another function that will calculate the flows at the each node given the function we just made, given the flows through each pipe. So we can call this function calculate, so calc, and we'll say calc net flow, and this will give in our flows argument, and we need to make sure that our net flows, we need to make sure those start with 0, just like we did in the function above. So we'll do the np.zeros once again, and then that will be for our number of nodes, so our n nodes. And then we need to do, basically what we need to do is add the 2 nodes to the flow and subtract the from nodes to the flow, since we're going with that direction. So the from nodes will be the negative. So we'll do that using something called np.add.at. And so for our net flow, we have our indices. In this case, for our 2 nodes, we're going to add them to our flows. So we'll have our 2 nodes for flows, and then we're going to subtract our from nodes. .add.add, and we'll do, so from our net flow, we have our from nodes. Then we do a negative flow, since the flow on the from node is negative. And then what we're going to want to return is our net flows, or net flow. And shift enter. And then what we're going to want to do next is, basically what we want to do is calculate the basically zero out what we did, kind of like the f to 0 function we did earlier. We basically want to zero out our internal flows given iterated through unknown internal pressures. And to do that, we kind of need to make we first need to make another import, and that will be a variation of the Newton function. In this case, it will be called root. So that's another function which is going to iterate through the unknown internal pressure values, and basically zero out our internal flows on each node. So basically what we need to do is we can set up another function, and this function is going to be the one that's going to be zeroing out our flows given unknown internal pressures that's going to be iterating through. So we have our net flow. We can call this net flow internal, since it's the internal flows. It's going to be zeroing out, and this will be taking the argument of unknown internal pressures and iterating through them. So we have unknown internal P, and then this is going to want to return our calculated net flow. So it's going to return our calculated net flow, which we had above. So calculated net Q, and then this net Q will be calculated based on the flow between each pipe. So then, given iterating through our head values through each node. So we'll have calc underscore flows, and then given iterated through our heads. So this will set up our function in order to calculate the or basically zero out our internal net flows given the some iterating through unknown internal pressures. So that's how we're going to set this function up. Okay, so we're going to end up calculating the net flows at our internal nodes, but before we do that, we're just going to go back up here and make a couple. Next what we need to do first is we need to specify what are our external and what are internal nodes. What are our internal nodes and which nodes are external? So basically what we need to do is we need to specify what our internal nodes are. And in this case, our internal nodes will be our total number of nodes minus our external nodes, in which we already specified up here, right here, external nodes 0 to 4 in our array. So we can say that we can put this in a list, and we'll set the range. So list set range, and this range will be the number of nodes, so our n nodes, And then, so this will be the number of nodes, and we said it was the number of nodes minus the range. Let me make sure these parentheses are on. Okay, so this will be the number of total nodes. Our internal nodes will be the number of total nodes minus the external nodes. So we'll set this other range to our external nodes, and this should give us our internal nodes. So we'll check. Okay, so yes, those will be our internal nodes. And our external ones, we already specified that they were the 0 and 4. So good, that gives us our internal nodes. And now what we're going to want to do is we also need to set our heads value equal to 0. So we're going to say that heads is equal to np.zeros. And then this will be in range of the number of nodes, not in range, just for the number of nodes that we have. So we'll have heads equals np.zeros, the number of nodes. And we also are going to need the heads at the external nodes. So we'll have heads at the external nodes, and to get this, basically our heads at external nodes will be our external pressure divided by rho, or density, divided by g. Plus our elevations at the external nodes. So we're going to go ahead and code that out. So our external nodes, our heads of external nodes will be the external pressure divided by rho divided by g, acceleration due to gravity, plus our elevations at the external nodes. So our z, elevation at external nodes, and that will be, which we specified earlier, this up here, which will be our elevation at our external nodes, which we specified. So we have, it'll just be 0 and 30, and our internal nodes are all 0. So that should give us our heads at our external nodes. So we'll shift into that. And now we can come down and finish coding out this function down here. What we're first going to need to do, basically when we think about it, we can do the same thing for the heads at the internal nodes in this, in our net flow function, by basically dividing by rho and g, given the internal pressure divided by rho divided by g, and then we can add the elevations. So that's what we're going to end up doing next to calculate the net flows at our internal nodes. So doing the same thing as up here with the external head, or the external nodes, sorry, the heads at the external nodes, we can do the same thing for the heads at the internal nodes, in which the unknown internal pressures are going to iterate through in order to calculate our net flow at our internal nodes. So to do this, we can do the same thing we did up there. So we have our heads at our internal nodes. We'll have our heads and specify these at our internal nodes. We're going to say that these can be equal to our internal pressure, internal pressures, can't spell today, internal pressure divided by our density and divided by our gravity, and then this will be plus our elevations at our internal nodes, not external. But if it was for external, like we did above, it would be external nodes. So plus our elevation at our internal nodes. Okay, so enter. And we can say that this needs to return the net flow that iterates through our values for our pipe flow, that iterates through unknown values of our internal pressures, given this equation for our internal our heads at our internal nodes. So we need to specify that this is in the internal nodes. Internal nodes. So we need to specify that these will be the net flows for our internal nodes. And so shift enter. Okay, and now that we have that, basically that will be the function that calculates the roots or the zeros of our internal nodes, given iterating through these unknown internal pressures right here. But to get a good initial guess, just like we did with the flow in our f to 0 function above, or earlier in this video, what we're going to want to do is we can make initial, we need an initial guess for our internal pressure. But to get an initial guess for our internal pressure, we can first make an initial guess of our internal heads. So we can just call this internal head guess. So our internal head guess, that is going to be, we can say that our internal head guess can be equal to the mean of our heads at the external nodes. So we're going to go do a numpy.mean, and we'll say that this could be equal to the heads, the mean of or average of the heads at our external nodes. And that's safe to say that that would be a good initial first guess. So we'll go ahead and enter that. And then from this internal head guess, we can get a good internal pressure guess, which then will help us calculate our flows. So internal pressure guess, we'll call this internal P guess, and that will be equal to our internal head guess, that will be equal to our internal head guess minus the elevations at our internal nodes times rho times g. So we just solve for this other equation for the internal pressure guess, except we could just have different variable names. So that would be minus the elevation at the internal nodes times rho times g, acceleration due to gravity. So that will give us our internal pressure guess from a good internal head guess, which would be the average of our heads at our external nodes. So now we can restore we can get our result in this from this root function. So we can just we can go ahead and check it. So result equals root, and these will be taking in our function, our net q internal. This will be taking in our flows, our net flows for the internal nodes, and iterating through our initial guess, which in this case it'll need to be iterating through our pressure. So we'll be iterating through our internal pressure guess, which we got from a good guess from the internal heads. I think I need to do result.x. Am I missing something here? Let me go ahead and try to run all. Okay, now it is really messed up. Looks like. Let me do a quick cut real quick. Okay, I think the error might work. There was like the Newton function I was testing up here. I just deleted this. I just deleted that Newton function. And this also was a parenthesis right there, I believe. There needs to be a parenthesis right there. And our root functions up here should be good. Yeah, that Newton function was like there was like a weird negative in there. So I just deleted it, and I think it should work now. But let's try. We have the result, so we just store this. So res.x and see what comes up. Result. Okay, so this, you can see that this gives us some values. But if we do result.x, this gives us our flows. And that will give us our internal flows that we're interested in. But basically, if we want to determine the other values within our pipe network through an array, we can do that as well. So we can see, we can go ahead and go heads. So what are our head values given these internal flows for our nodes? So this will be our first internal flow, or for node 1, and then we have node 2, and then we have node 3. So those will be our internal flows given this initial gust for internal pressure, and calculated through our the pipe flows that we calculated. So all we need to do next is basically isolate the other arrays. So we have what are our calculated flows through each pipe given certain heads. What would those be? And that's what those values would be. You can see that at the last node that it becomes negative, our calculated flow for that pipe. So we have pipe 1, 2, 3, 4, 5, and 6 pipes. And what are our calculated net flows through each nodes, given the calculated flows through the pipes, given certain heads? And that is what we will be looking for. So what are those? That will be calc flows. Our calculated net flows internally from the calculated flows through the pipes given certain heads. And that should come up with this array. And that will give us our calculated net flows through each pipe. So now we have an answer. This looks good. And that completes our pipe network.